Assalamu alaikum. Today we will be discussing the serviceability of reinforced concrete structures, and we will be talking about crack and deflection control. And as we see, the word control is key. We really can't eliminate deflection and cracks 100%, but we will try to control them as much as we can. And during this course of this class, we will teach you some of the techniques used to control both crack and deflection, although we will tackle today only the crack control and talk about deflection in our following class. Now, serviceability again, crack and deflection control. Now, all the serviceability studies are carried out based on elastic theory. Okay, so Hooke's law applies. Stress is equal to E times epsilon strain. Concrete may be assumed to be uncracked, partially cracked, or fully cracked, and we had full discussions of that when we talked about the design for flexure back in chapter 3 of the text. The methods that will be developed will ensure that the cracks associated with flexure of reinforced concretes are narrow and well distributed, and the short and long-term deflections at loads up to the full service load are not objectionably large. Okay, again, it's all about the control, not the elimination of both cracks and the deflection. Now, again, as I said, we're going to start with crack, and now we're going to discuss the factors that influence the width of the crack. The first factor would be the bond between the steel and concrete. Now, if we have smooth round bars, we will see smaller number but wide cracks. Now, on the other hand, bars with surface deformation, and these are the surface deformations that we are talking about, these right here, these will ensure a better bond, obviously, between the concrete and the steel, and it also will lead to a larger number, but very fine, almost invisible cracks, as we call these. These act more like what we call crack arresters, which prevents the crack from moving forwards from point to point. The other influence, the width of crack, is obviously the stress in the reinforcement. And the crack width is proportional to the stress, meaning if the stress increases, then so would the width of the crack increase. And we can calculate this stress using our techniques that we again taught you back in chapter 3, and I will show you the example at the end of this lecture how to calculate Fs, or we could just take it as 2/3 of Fy, or 2/3 of the yield strength of the steel. Okay. Other factors is the concrete cover distance, which is measured from the center of the bar to the face of the concrete. So if this is my lower section, I have a bar here, then I'm talking about this distance, the center from this, and this will be my DC. Again, increasing this distance will increase the width and the spacing of the crack. The distribution of the reinforcement in the tension zone, and that's what we usually like to do. We like to use a larger number of smaller diameter bar to provide the required area of steel than to use minimum number of large numbers. So probably I would like to use, let's say, a 5 Phi 20 instead maybe a 3 Phi 25. Again, by doing that, you're using less spacing between bars. The fatigue also will increase the crack width, especially when we have cyclic and sustained loading, but it will not, in some experiments shown, it will not add to the number of cracks developed. It only will lead to the increase in the width of the crack. Now, there are two famous equations that predict the crack width, and these are all based on statistical analysis, more or less like by doing regression. You design certain beams, you experiment on them, and then you measure the crack width, and then you come up with an equation. And these two famous equations are, one is by Gregley and Lutz, and the other is by Froch. I hope I'm not butchering their names, but and these are, by the way, based on SI units, and I will get to what beta and FS, DC, and the area means on the next slide. So here, this will kind of explain the equation. So first of all, the width, or W, of the crack in the equation is the maximum width of crack, and the result is in thousands of millimeters. Fs is the stress, the steel stress at load for which the crack is to be determined, and it is in megapascals. Okay, so megapascals or Newton per millimeter square. E is the modulus of elasticity, again megapascal. Again, for regression equations, you always have to make sure that you're using the consistent and right units, or the factors in these equations will be wrong. DC is the thickness of concrete cover measured from the tension face to the center of the bar closest to the face, as I showed you before. So this is DC right here. It is to the center of the first bar. Beta is equal to H2 over H1. Now H2 is the distance from the neutral axis to the outmost tension fiber, which is right here. H1 is distance from the neutral axis to the center of the reinforcement. So if I had, let's say, one layer of reinforcement instead of two, then this would be my H1. Area is the, or A, sorry, is the concrete area surrounding one bar, equal to the total effective tension area of concrete surrounding reinforcement and having same centroid divided by number of bars in millimeters square. So if you look at the figure above, so now Y is the distance to the center of the reinforcement. So having two layers right here, this will be my center. Okay, then area, my area would simply be equal to 2y times the width, B web, divide that by number of steel reinforcement. In our case, we have 1, 2, 3, 4, 5, 6. So divide that by 6. So this would be my A. Then S would be my maximum bar spacing in millimeters, and here is the width that we are talking about. And I will give an example at the end of this lecture of how to use this equation in great details. So, as far as the provisions for crack control in the ACI code, the ACI 2019, we will find that in section 24.3. As I said in previous lectures, I'm only giving you part of the code which concern us the most, in case if down the road some changes, as it usually does with the code, you will exactly know where to look for them. So again, section 24 deals with the distribution of flexural reinforcement in one-way slabs and beams. Okay, so this is only applicable to beams and one-way slabs. Now, the bonded reinforcement shall be distributed to control flexural cracking in tension zones of non-pre-stressed and Class C pre-stressed slabs. Since we're not talking about pre-stressed slab in this course, we will only concentrate on the reinforced concrete. And again, it's beams and flexure in one direction only. Spacing of bonded reinforcement closest to the tension face shall not exceed the limits of table 24.3.2, which we will see on the next slide. CC is the distance from the surface of deformed or pre-stressed reinforcement to the tension face. Okay, now remember in the equation we had the distance DC, which was to the center of the reinforcement, and this was my DC. Now the code says I'm not going to the center of the reinforcement, I'm going to the bottom of the reinforcement and call this CC. And by that, what they're doing, actually, they are taking the influence of the bar size on the spacing control, which means that for larger bars, we probably would have wider cracks. Okay. The calculated stress in deformed reinforcement FS shall be in accordance with section 24.3.21 and 24.322 respectively. For us, we are only concerned again with reinforced concrete, not pre-stressed, so we will be concentrating on this section right here. Now, the equation or the table that we're talking about, so my maximum spacing, S, should be the lesser of this equation right here and this equation right here. So this is simply 380 times 280 divided by Fs minus 2.5 cc, and we already showed you what cc is, or just 300 times 280 over Fs. So, and the rest we really are not concerned for this class. Again, so the maximum spacing should not be more than this equation right here or this equation. So we will calculate them from this one and that one, and then take the lesser value. Okay, now going back to the calculated Fs. So Fs is closest to the tension face. Okay, so what does that mean? So if this is the bottom of my section, and let's say I have one layer here, and I have another layer here and another layer here, my Fs will be calculated for this part right there, which is the last layer. Even if I have fourth layer or third layer, sorry, then Fs will be calculated at this layer right here. Or if you do not want to calculate Fs at all, it is permissible just to use it as 2/3 of Fy. So let's say you have a grade 60 or Fy is 420, then 2/3 of that will be your Fs, and you don't have to do anything more. Now, why this equation? Well, if we look at the equations developed by Gregley and Fruchs, which were equation 1 and 2, you can see that if we draw the bar spacing S versus the clear cover CC, they meet only at 2 points here and here, and they're widely different everywhere else. So as a compromise, as I said, I'm gonna come up with a new equation that kind of will take those two in perspective, and hence this is my table 24.32. As you can see, they are giving you more spacings or larger spacing than the other two equations. Now, these equations were carried out based on width or crack width of 0.4 millimeters, Fs 280, beta 1.2, and we used 1 phi of 25, so that we were able to generate these two figures, or these two figures right there. Okay, for equation 1 and equation 2, I'm comparing that to table 24.3. Now, there are some additional provisions for crack control that I need to mention right now, and they are related to T-beam. So what happens if, so as you know, when we took the part for designing T-beams, and excuse my drawing right there, well, actually I don't like that, so I'm just going to take that out. Hopefully I can do a better job this time around. So this is right there, here, here. Okay, so for my T-beam, when this area is in compression and my steel is here in the bottom, all right, then I usually don't have any problem with dealing with spacing. But what happens if this is part of a continuous beam or continuous slab, then we will have, when we go to the negative moment, right, negative M, then this now will be your compression phase, and this now will be under tension, the whole part. But if I'm going to limit my reinforcement to B web, then I cannot leave those sections without any reinforcement. So again comes the question, so how much of a distance should I go? And that goes back to the definition of the effective flange width that we tackled back again in the design for T-beams, which talked about section 6.32, the same table that I've shown you. So then I will compare that with the distance, the clear distance between supports divided by 10, and take the lesser value of those. Now, if this controls, then I need additional longitudinal reinforcements satisfying 24.3, which shall be on the next slide, which means I need to add another longitudinal reinforcement in this direction, provided that this controls. Okay. Now, the deformed reinforcement to resist shrinkage and temperature threshold conform to table 20.2, and I will leave this table only talks about the maximum grade of steel I can use for design. So there's in some instances, even if I, let's say, have a grade steel of 690, for instance, I cannot use more than 550 in the design process. But I will leave that table to when we start talking about the development length, so you should not be concerned with it at the time being. The amount of steel that I need to use of the longitudinal reinforcement should not be more than, or the minimum should be 0.0018 area gross as a reinforced, which is probably my shrinkage and temperature reinforcement. The spacing for this should not exceed the lesser of 5H and 450 millimeters. I mean the total height of the cross section. At all section where required deformed reinforcement used to resist shrinkage and temperature shall develop FY in tension, which means I have to satisfy the development length, which again we're going to talk about probably soon. Okay, well, soon I mean maybe 2 weeks. All right, so these are additional provisions for sections. There's another provision also when the height of the cross section is more than 900 millimeters, then I have to provide what we call skin friction, which are right here. The spacing, and these are usually distributed over H over 2. The spacing S should not exceed the maximum allowable spacing that we have calculated from using table 24. So have you seen by now, when we start talking about the flexure, we had minimum spacing of, let's say, 25 millimeters and the diameter of the bar, and now we have a cap, which is a maximum spacing. So my spacing should be within the range of the minimum spacing and the maximum spacing, and the maximum spacing is actually controlled by the crack width due to the crack control. And that will lead me now to an example. In this example, the figure below shows the main flexure reinforcement at midspan for a T-girder in a high-rise building that carries a service load of 880 kilonewton meters. Please note that for any crack control deflection calculations, we only use service loads. There are no ultimate loads involved whatsoever. Okay. Now, the clear cover on the side and bottom of the beam stem is 60 millimeters. So this is the side cover, and then this is the bottom cover. Determine if the beam meets the crack control criteria in the ACI code. Use FY 420 megapascals. As you can see, I have 10 Phi 25. Here I'm using the cover of 60 millimeters. Add to it the Phi 25 over 2, and that's why you're getting here 72.5 millimeters. And since I have here 2 layers of steel, then my D is simply 900 minus 72.5 plus 25. Okay, and you will get 805. To check the crack control, first of all, I'm going to use, I'll calculate Fs, and this is going to be my service moment, which was 880 kilonewton meters. Here I'm multiplying by 1000 to make it newtons and another 1,000 to make it millimeters. The 4,908.73 is simply the area of steel. D minus the height of a flange of 2 will be 730. So Fs is equal to 245 Newton per millimeter square. Or I could just bypass this whole thing and just said, hey, you know what? I'm just going to take Fs to be 2/3 Fy, and which is equal to 280. Now I'm going to calculate the maximum spacing S, which is 380 times 280 over Fs minus 2.5 cc, and that will be equal to 380 times 280 divided by 245 minus 2.5 times 60. Again, this is my cc right here, which is my 60 millimeters, and that gave me 283.26 millimeters. Now you should do that on your own. You should also compare that with, which is giving me this to be my controlling. You should compare this also to 300 times 280 divided by 245, and this value is lesser than that value. I mean, if you only take in 2/3, then obviously this is the lesser value. So S is 283.26. Now the 110 millimeters I calculated based on what we have here, which is just simply taking the 685 minus 2 times 60 minus 5 times 25 minus 4 times S, and from that you can calculate S. So this is, yes, it is okay. So this is kind of conforming to my ACI crack width. Now, in another example, he wants, and this is going to be the last one, he wants us to use the Gregory-Lutz equation to estimate the maximum crack width at the moment equal to 100 kilonewton-meter for the beam cross-section shown here. All right, this is an old example that we solved back in the design for lecture. Still, I'm using the same 3525. The width is 255 millimeters. Height is 650. D is 600. Here I have the rupture stress Fy F prime C. I'm not going to check whether it's cracked or not because we already know it was cracked from example, as I said, I2 at the pi. But here I'm just taking the values for K, Y bar, and bypassing the calculation again, since again we have already done this, right? But again, if you want to, the details is here. This is the equation for K. We know what Y bar is. N was equal to 8. This is my rho, and then I calculated Fs to be 152.5 megapascal. Okay. So now moving on. So to help us in the calculations, I added these two figures. So first of all, we're going to start with finding DC. Again, DC is the distance from the outmost tension phase to the center of the reinforcement. And in that case, it would be H minus D, and that will give me 50 millimeters. Now moving on to calculating beta. For that I need H2 and H1. H2 now is the distance from the neutral axis up to the utmost fiber of the tension phase. So it will be simply 650 H minus my Y bar, which is 195.3, and that will give me 454.7. H1, on the other hand, is the distance from the neutral axis to the center of the reinforcement. In our case, since we have only one layer of reinforcement, so that will be simply D minus Y bar, and that will give me 404.7, giving me a value of 1.12. Now A, again, which is the area around surrounding the reinforcement. Here I have only one layer, so now this would be my Y times that, which we found to be 50, times that by 2 to get the total area, times the B web, or B, which is this one right here, divide that by the number of reinforcement, the 525, So this is 3, so this is the total area that I'm getting in millimeters square. Now just going in, plugging this into the equation, then the width will be equal to 1.1 times 1.12, which was my beta, times my Fs, 152.5, times the cubic root of DC times the area, 833 times 10 to the minus 5, and the answer would be 0.14 thousandths of a millimeter, or simply put 0.000 or 14 thousandths of a millimeter. Okay, so this is 14 thousandths, or 10 thousandths of a millimeter. So this will end my presentation of my class for today. Hopefully I will provide you with the second part sometime this week.